All right, so welcome to Math 119-312. It is wonderful to finally have some students in the room again. So I am Professor Miller. Feel free to call me Steve. This is a non-standard class. Normally I use the title professor, but this is an all hands on deck. We're all in this together. Whatever you're comfortable with is absolutely fine. Still dealing with the technology. Unfortunately, it is not allowing me to project as it's supposed to, so I will not be able to use the pen. So I will have to use scribbly notes with my hand. This is a really good opportunity to talk about you always have a backup plan. So if something doesn't work, you have a fallback. This is why I do have slides prepared for today, just in case I wasn't able to write, because we have people taking this both in person and at home. All right, so let's see. So what I want to talk about today is a little bit of statistics again, and just really driving home how easy it is to manipulate things. And then from that, I want to start talking a little bit about simple mathematical models. So how many people here have read the comic strip XKCD? All right, so I see a bunch of people have read that. This is one of my absolute favorites. And so one of my friends sent this to me recently. Apparently some university reopened based on COVID model developed by two physicists. But even their worst case model underestimated the number of student parties and they had to shut down. I can't understand why someone with a physics degree would be bad at judging how often college students get invited to parties. Excuse me, I was invited to multiple parties and attended both. So this is a really good point to make. When you are creating your mathematical model, what are you including? What are your biases? How do you determine what to put in and what not to? Shouldn't we include everything that's important? So should we include everything that could possibly have an impact? Why not? Too many things, right? There is a trade-off. The more things you include, the more complicated your model is, and the less likely you are to be able to do anything useful with it. We want a model that is complex enough to capture what's going on, but not so complex that we can't solve it. And this is going to be a terrible trade-off that we're going to have to decide on. For some things, it's going to be very easy. Anybody know some of the most famous physics experiments of all time? Any physics people here? Galileo, what is the experiment?
Dropping the two balls
Anybody know
from
the experiment Galileo did?
Top of the tower?
He had two spheres, and he wanted to see if the time it takes to land is a function of the mass of the ball. How many of you have heard of this experiment? Excellent. So this has been passed down from generation to generation. What color were they? No one knows. Why don't we know? It is probably irrelevant, or at least it's irrelevant to the main term. One of the problems could be, what if the different colors, one absorbs heat well, and one does not? So maybe one is now very hot, being left out in the sun, and one is cold. Maybe as you drop, an object that is hotter could actually have a different falling path than an object that's colder. And this is one of the dangers of correlations versus causations. So when you have a lot of things going on, you might misinterpret what is really driving what is happening. Now, if they were both kept indoors and they both have the same temperature, and then you release them, it doesn't matter what color either one is. That will have absolutely nothing to do with the physics. But if they were different temperatures, that could have an impact. So when you're trying to create your mathematical models, you really have to think, what do I need? Okay? So I have included, two other XKCD ones. I used to think correlation implied causation. Then I took a statistics class, now I don't. Sounds like the class helped. Well, and if you're an XKCD fan, if you actually roll over and put your mouse on the comic strip, it actually gives you an extra special geeky joke. The other one, which I really like, is two people are talking, and one says to the other, I think we should give it another shot. You're talking about their relationship. And the other one is, no, I think we should break up. And so there is a nice plot of their relationship. And the person goes, maybe you're right. I knew the data would convince you. No, I think I can do better than someone who doesn't label for that. Whenever you see a plot or a picture, I always want you to be thinking, what is the units? What is the scale? What is being studied? And a lot of times, what if this is going from 9.9 to 9.91? That's really not much of a change. And so depending on how you want to play with things, you can easily put up charts showing wild movement, depending on where you zoom in and where you stop. So just be aware of issues like this. Okay. So here is a little experiment that I would like to do. And so we'll split it up into two groups. We will do the class that is here live and you can talk amongst yourselves. And then the people who are at home, you are still allowed to talk to each other, right? That's not been removed. Yes? Okay, good. So you can talk to each other and order them in increasing order. From alcohol, so least to most deaths per year. Alcohol from drunk driving, breast cancer, cardiovascular, drowning, flu, medical error, pregnancy, delivery, prostate cancer. So we're going to have a competition between the in-person class and those who are home today.
Should we include coronavirus?
One is closest is excused from one homework problem for the rest of the semester. You can use whenever you want. Yes. So good question. Yes. I know it's extremely important because one of the items I almost added was death by hunger. And I'm not adding that because in the US, it's actually so low, it's not worth putting in the list. But that's a really good question to ask. There's a lot of websites where they talk about creating random stories. And you have a monkey just padding away at a typewriter. And if the monkey just hits the keys randomly, it's crap. But if the mathematicians come in and help the monkey, it's a different story. So what you can do is after the monkey hits the T, you give the monkey a special keyboard that has the letters at different frequency, the frequency that follows the T keyboard. And this is called a first order monkey. What do you think a second order monkey would be? So first order, you look at the last letter typed, and that influences the next letter. The last two letters typed. What do you think the third order monkey would be? Right, so it's pretty clear. By the time you get to a fourth order monkey, it's actually reasonable. And what you can do is you can have different types of monkeys. You could have the Edgar Allan Poe monkey. You could have the William Shakespeare monkey. You could have the Arnold Schwarzenegger monkey. You could have very different monkeys. And depending on what text you use to train the monkey, you will have very different language coming out. So the question of where is this coming from? Excellent question to ask. All right, so you guys have a slight disadvantage because you have fewer people than the people online. So if there's a tie, you will win because of home field advantage. All right, so I'm going to give people I'll give people 3 minutes to think about this. So for those of you who are at home and watching, use the chat session, talk amongst yourselves. Somebody at home has to step up and take charges. I will be the person who will be submitting the answer. I'm going to hit pause on the recording right now.
Stephen, why don't you appoint a...
We will resume recording. All right. Greetings to all of those who are out watching this through Zoom. Do we have a spokesperson?
Yeah, I can read them off.
Wow, there's now 70. Okay, there's 70 on the list. Excellent. All right. Do we have somebody who's going to be the spokesperson who wants to speak?
Yeah, I'll read them off.
Or can the people online, can you rewrite your list? Not change your list, just write it down. Me. I cannot hear people, so if people from online are trying to talk, let me. Can people? Can people online hear me now?
Yes.
Okay,
Yeah.
can one of you give me your list? I'll put it in the chat.
Yeah, it's in the Zoom group chat. I put it from most to least. I'll put it in least to most.
Thank you. Thank you. Oh, wait. Did anybody, wait, did those in the chat Google? Wait. Was there Googling? Did people in the chat Google, yes or no? Okay, I'm hearing many no's. It technically wasn't said you can't Google, it was just assumed. No, yes, no. All right, so let's look at the chat. So the list is, okay, so wait, you gotta put it in the opposite order?
I put them in both orders.
As the least or the most?
So the most recent one at 10:55 was.
Okay, no, there's no still working. All right. So let's do the answers. About 700 women die each year as a result of pregnancy or delivery complications. 788 drowning deaths. In 2018, 10,511 people were killed in alcohol-impaired crashes. Preliminary data suggests around 24,000 to 62,000 flu deaths. There was an estimated 31,620 deaths from prostate cancer. Approximately 42,000 people died from breast cancer. 251,454 deaths from medical error. And then about one person dies every 36 seconds from cardiovascular disease, or about 655. So we will look to see how many in a row you got. So if you started with medical error, unfortunately online that is a 0. Medical error was actually significantly higher. It was the second highest of the elements listed. So the people here started off with pregnancy, which was correct, and drowning, alcohol, so the first two was correct, and then medical error and flu. If you had switched those, you would have had one more. So the purpose of this exercise is to just give you a sense of different magnitudes, different numbers. So my primary training is as an analytic number theorist. The material I learned as an analytic number theorist is not the most useful for teaching this class, okay? The training I have as a mathematician, absolutely useful. So anybody know any theorems about prime numbers? Yes. There are infinitely many prime numbers, and this goes all the way back to over 2,000 years to the ancient Greek geometries. The copyright has easily expired. It's one of the most used classic proofs in high school and college. If I give you a prime with 25 quadrillion digits, it may seem like a large number, but relative to infinity, it's a drop in the bucket. One of my friends wrote a wonderful book on trying to get a grasp of just how many ways there are to do things, how quickly some numbers grow. And when you hear things, especially in the news, I want you to try to get a sense of how to put numbers in perspective. So there's the old saying, one death is a tragedy, a million is a statistic. I want some kind of balance between those two polar extremes. I don't want us to ever forget the real suffering that's happening. But at the same time, there's a lot of suffering going on in many different ways, and we're going to have to compare, unfortunately, apples and oranges. And we're going to have to make very difficult policy decisions that have trade-offs. And you want to try to get a sense of, well, just how many people are we talking about? How large is it? So in terms of, right now, how many people have died from COVID in the United States, the official count is a little bit under 200,000. But we will talk later in the semester as to what do we mean by the official count. And just how accurate all of these statistics. I actually like the fact that for the number of flu deaths, it's some kind of range 24,000 to 62,000. Ending with 3 zeros, so this is not an exact count. This is trying to estimate what we think might be going on with all the other factors in play. do you think the alcohol statistic is a reasonable one to be that accurate, 10,511? Yeah, these are probably being reported, and so there should be some way to get that. You know, you may miss some because there could be something going on, and you may not know that alcohol was responsible for the death, depending on how things happen. I was almost killed years ago by a can of Diet Dr. Pepper. So I was visiting some friends at Dartmouth, and I was driving to Boston the next day. It was a bad snowstorm. I'm completely focused on the road. And then as I'm driving in the storm, I hear gunshots in my car. And my first thought is, I wonder who's trying to shoot me in my car. But I fortunately just keep driving there. I wonder what's going on. And eventually I realized what happened. I had parked the car outside, and it was really cold, and I had a can or two of Diet Dr. Pepper in the back of my car, and it froze. And as I was driving, it expanded, and the top of the can just shot off. And so it would have been fascinating. It would have been interesting if I had died as to how they would have classified the death. The most natural classification is it was bad weather, there was a blizzard. Why was the stupid idiot driving to give a math talk in Boston? Who the hell cares? Just don't give the talk. But what really would have caused it would have been a can of Diet Dr. Pepper. So you really have to be careful when you look at a lot of these statistics. What is really driving what's really going on? Okay. So the next is I want to talk a little bit about Fibonacci numbers. And the reason is I want to do a little bit of introduction to mathematical modeling. So the very first thing you should do when you model is you do the simplest thing possible. If you cannot solve the simple problem, you have basically no chance of the more complicated model. Then you start adding features. And say, okay, now that I can do this, let me introduce this. I realize that this is an unrealistic assumption. But if I can't even do this, I have no chance of doing anything else, so let's see how well I can do. Okay, so I am not going to play this video. I strongly encourage you to watch it if you like Fibonacci numbers. It actually talks about an application of a generalization of the Fibonacci numbers to gambling, to the strategy double plus one in Las Vegas. I made this years ago with OIT and some students. I would never, ever make a video like this again. I gave the lecture in an empty classroom. And there is a huge difference when you are talking in an empty classroom and when you're physically talking with people present. The interactions, the dialogue, it's completely different. And so it's almost worth watching just for the humorous view of how I am standing and talking without anybody there and without anybody to feed on. Anybody a fan of America's Got Talent? Oh, thank you. Okay, you are now exempted from one homework problem for any time in the semester. Thank you. My kids are younger than you by a couple of years. I know the cultural connections are not going to go as well, but America's Got someone, American Ninja Warrior? A little bit more than that. I was entertaining. Okay, the original, that's fine. Your British Got Talent, also great show. But if you watch America's Got Talent now, for some of the rounds, the performers have to go without an audience. For some of the performers, it makes no difference. For a comedian, it is very hard to do your routine. And of course, I don't view this as a team. It's very hard to do your routine without an audience and just how you change in those situations. So there's a lot of good math in this that explains a lot of what I'm going to do in greater detail. So here is a image ripped from the web without any concern. And so here's a simple way of doing the Fibonacci numbers. Actually, as long as I'm not going to be using my pen because that's not working, I might as well go to full screen. Right. So the way it works is the following. We're always going to talk about pairs rather than about individuals because that makes more sense when we're trying to talk about how many things have grown. Right. So do not worry about people meeting with their siblings. We're just going to do this for mathematical simplicity. Right? If you are alive, you move on to the next level and you stay alive. If you are at least 1 year old, you give birth to one pair. So that is the rules governing this sequence. And we can ask, if we start with one pair, how many pairs will we have at any later time? Well, if we start with one pair, it was just born, so the only thing that can happen is it gets older by 1 year. Now that it's 1 year old, it survives, and it gives birth to a new pair, and they were kind enough to draw them with slightly different colors. This pair is now 2 years old. It can now give birth to another pair, and it survives. This pair, however, was just born, and it can't give birth to anybody else, so it just survives. And then at the next level, this pair can now give birth, this pair can give birth, they both survive, and this one survives. And so you get a sequence 1, 1, 2, 3, 5. And so if you have never seen this sequence before, if you've never seen the Fibonacci's, does anybody have any guess as to what the next level might be? You know, look at the chat as well in case anybody wants to guess from the chat. Or has everybody seen the Fibonacci's? So I think everybody might have seen the Fibonacci's. So the next number would be 8, then 13, 21, 34. Okay. So here's the first couple of Fibonacci's. And there's a couple of different ways to define them, as I am defining them here, 0, 1, 1, 2, 3. For some people who I know in the audience, I understand that there are other ways you can define them. The rule is the n plus first term is the sum of the two previous. So this is our first example of a very simple mathematical model. So Fn is going to be how many rabbits we have at time n. And the number of rabbits we have at time n plus 1 is the number of rabbits we had at time n plus the number of rabbits we had at time n minus 1. And that makes sense because if you think about this, the assumption we have is that if you were just born, you were not able to give birth to a new pair. So those who were just born can't give birth, but those who have been around can give birth, which we need to track a little bit. All right. So there's a lot of questions you can ask. Is it easy or hard to find a given Fibonacci number? If I asked you to find the 20th Fibonacci number, could you do that? Yeah, the previous two. What if I asked you to find the billionth Fibonacci number? Is it easy or hard? Why is it hard? Yes. So if we use this definition, if we want to calculate the billionth, we have to keep going through everything. Now, it's not a horrible problem. We're just adding. We have to do it a lot. But if you write a computer program, you only have to keep track of the last two additions, the last two summons, and you can just march, 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 march. But if I wanted to calculate the trillionth, the quadrillionth, you will eventually overflow what the computer is able to do if you do it by brute force. And then last, another question, is there perhaps a better way to do this? Is there a way to circumvent the calculation? So depending on how complicated your mathematical model is, we might actually have to do things to help the computer run in a reasonable amount of time. And that's one of the reasons why I wanted to bring this issue up right now. It's a very simple formula. Add the two previous. Could we train somebody in 6th grade to do this? Yes. And in fact, I have someone at home who can train. Okay? It's not going to be fun, but we can do it. So the question is there an explicit formula? Another question is, what are the applications? And so there's a wonderful video, Nature by Numbers, that I encourage you to look at. And then the last is, how can we generalize the Fibonacci numbers? Now, before I talk about answering these questions, I want to go back to this model. So I said, keep it simple. So the number you have at time n plus 1 is the number you had at time n plus the number you had at time n minus 1. Is this a reasonable model? So what concerns do you have about this model? Yes? No rabbits die. These are immortal rabbits. That could be a technical. Yes. They could have more than 2 offspring. Any other issues? Great, I love that phrase. The environment can sustain an ever-increasing number of rabbits. That at some point, when we get to maybe the billionth, trillionth rabbit, there may be some issues in terms of, is there a food supply? We may even have issues in terms of space, in terms of where you put the new ones. So there's a lot of issues with this model. How could you fix it? Any simple ways to fix it? I'm sorry? So how would we try to provide those limitations? So we want to somehow change the model. And you don't have to give me the math speak. You can just say what you want to have happen. Good, so maybe rabbits die. And so the simplest thing is to just say all rabbits die at a certain time. If that is, a little bit too simplistic, you can start having maybe some number of rabbits die after living 3 years, after 4 years, after 5 years. So you can start introducing features to the model. Okay, so now there is a beautiful way to mathematically solve this. And so we can write down a closed form solution. That's actually one of my favorite formulas in all of mathematics. So what we're going to do is we're going to guess. And so we're going to guess fn plus 1 is fn plus fn minus 1. We have our recurrence here, and we're going to guess that fn is r to the nth power. So the question is, why is this a reasonable guess? And so, let me see if I can just quickly change screen on. Okay. So unfortunately, it's not letting me use my social note. So what we have over here, n plus 1. Whoa. Interesting font. We have fn plus 1 is fn plus fn minus 1. And we want to try to get a sense of how rapidly is this growing. Is this large enough so people can see? So since the sequence is increasing, we know fn plus 1 is going to be less than or equal to fn plus fn, which is twice fn. Does that make sense? Because the sequence isn't getting smaller, I know fn plus 1 is less than twice fn. So that means every time I go forward one step, I at most double the number of rabbits. So we know fn goes no faster than 2 to the n. So we have an upper bound. So this is something I love to do. Whenever you have a problem, can you give me some features of the system that you're studying? Can you give me some idea of order of magnitude? Now, similarly, if you go in the other direction, we know fn plus 1 is going to be greater than or equal to 2 fn minus 1. And we can use this to get a lower bound. And after some algebra, we get fn is greater than or equal to square root of 2 to the n. Square root of 2 to the n less than or equal to fn equal to 2 to the n. Algebra might be a little bit off, but roughly this is what's going on. Yes? The square root of 2 raised to the nth power. Of course, if I bring the n inside, it's the same way. So I'm taking the number root 2 and I'm raising it to the nth power. So another way of saying this is about 1.414 to the n less than or equal to f of n less than or equal to 2.000 to the n. So what we've done by a simple calculation like this is we've shown that fn is growing exponentially fast, geometrically fast. We don't know the correct growth rate. We know it's growing at least as fast as every 2 iterations, it at least doubles. And every one iteration, it does not fully double. So it's somewhere between 1 and 2 iterations is needed to double. And so this gives us some hope that what we were doing here was actually a good idea. We were going to guess that Fn is equal to R to the n. Is we just don't know what that growth rate is. Let's see if this works. This is my favorite method of solving a math problem. It's called the method of divine inspiration. You essentially write down the answer, and then you show the answer is correct. What is the problem with the method of divine inspiration? I'm sorry? So good, so one possibility is there could be more than one answer for a problem, and you might only see one answer. What else is the problem with divine inspiration? Yes? You have to, well, not lucky, you have to be divinely inspired. Not everyone is always divinely inspired. But for those of you who take computer science, it's often a huge different theory between trying to find an answer and verify an answer that someone gives you. And so the idea of trying to guess R to the n is the solution. Well, if I put that into this relation, I'll get R to the n plus 1 is R to the n plus R to the n minus 1. This is fun with the Boston accent. So we divide both sides by R to the n minus 1, and we get R squared equals R plus 1. This is a quadratic polynomial, degree 2. This is the quadratic formula we can solve. And we get the roots are 1 plus or minus root 5 over 2. And then you start doing a few more things. You say, well, you know what? If instead of guessing R to the n, if I tried 3 times R to the n, I would just multiply everything by 3 and it would still work. Or I could multiply things by 5 and it would still work. Or I could take the root, let's call the one with the plus sign R1, let's call the one with the minus sign R2, and I can take any combination of them, and this is just go through and do the algebra. Just plug this in and show that that satisfies this relation. So for any choice of C1 and C2, this works. And then what we do is we choose C1 and C2 that match the initial conditions. So we know when n equals 0, we should get 0. When n equals 1, we should get 1. When the dust settles, you get 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. We have an explicit formula now. So think back to when I told you to find the millionth Fibonacci number. We no longer have to go through all of them. We can just jump to the answer. What kind of numbers are the Fibonacci numbers? Yes. They're integers. When you look at this, if there was a police lineup and say, some number mugged you, and they have a bunch of numbers as suspects and you're looking at them, does this look like an integer? You've got division by 2, you've got square roots. Everything cancels, and at the end of the day, it's an integer. More is true, which is nice. 1 plus root 5 over 2, that's about 1.6. 1 minus root 5 over 2, this is less than 1 in absolute value. What happens if you take a number less than 1 in absolute value and you keep raising it to a higher and higher power? So I have 1/2, 1/4, 1/8, 1/16. What's this going to? It approaches 0. So what I love about this is the main term, and this is a lower order effect that does not matter. We have a lot of rich alums online. I hope one of them is about to donate $1 million to a lucky student in this class. If so, please let me know. I only take 10% processing fee. If you are about to get $1 million, are you happy? If not, please let me know, because then we should absolutely talk about that's not enough to make you happy. Most people, I assume, would be happy if you get $1 million. What if I then tell you, oh wait, I forgot, it costs $1,000 to process this. You're gonna have to give back $1,000 out of the $1 million. Do you even notice the $1,000? No, it's noise. And so when you're looking at complicated models, complicated systems, you want to try to get a sense, where's the beef? Where's the main part that matters? And what is the part that I can safely ignore? This is so small when n is large, I can just ignore this. I don't really care about this part. In particular, since the Fibonacci numbers are integers, and this is going to 0, the nth Fibonacci number is whatever integer is closest to this. I actually don't have to calculate the second one. I just need the first one and just take the integer closest to that. So there's a lot of wonderful things we can learn, just by looking at this problem. So we're already seeing main terms and lower order terms, and that we can hopefully try to ignore the lower order terms. Sometimes you can get explicit formulas, wonderful stuff. All right. So just as a personal aside, for those of you who are interested, I do run math research programs over the summer. At least one person here has already worked with me on papers related to the Fibonacci numbers. I am one of the 12 people, I'm sorry, we're now 13 people. That was one of my accomplishments. I increased the number of people on the Fibonacci board to 13. Why do you think I wanted to do this? Yeah, the 13 is a Fibonacci number, 12 is not. I said, either we have to make Leonardo, Fibonacci an honorary member of the board, or we have to get somebody else. And they decided to get someone else, which is fine. Also, for more Rubik's Cube stuff, this is a nice cube with the Fibonacci spiral coming in. Lots of great math here. Okay. So because it took me longer than I had hoped to set things up, I did not play the music at the start of class, but I will show an image from a 1980s movie. Cultural extra credit, and I'll look at the chat. Anybody know what movie this is from? If you think you know, just raise your hand. It's a science fiction movie that involves whales. No. So it is from Star Trek IV, which was actually a funny Star Trek movie. It's too complicated to explain why, but briefly, as best as I can, there's an alien probe that's pissed off that we killed off the whales, and so they're going to destroy all of life on the Earth and redo things. So in order to stop that, we have two options. One is to defeat the probe, which we can, it's destroyed our entire fleet. And the other is to travel back in time to when wheels exist, bring back two wheels to talk to the probe and say, please give humanity another chance. And so we go with option 2. And so the idea is to bring back wheels to repopulate the species. And so this is a modification of the Fibonacci rabbits. So what I'll assume now is when a wheel pair is born, they do nothing. When they're 1 year old, they give birth to 2 new wheel pairs. When a wheel pair is 2 years old, they give birth to 1 pair. You're getting a little bit older. When they're 3, they basically just enjoy life. And when they're 4, they die. Or if you want, if that's too gruesome, they are then taken by the probe to a nice planet for wheels, and are just no longer on the Earth. So no wheels are harmed in this exercise. Is this a reasonable model? Are there things you like about it? Are there things you don't like about it? What's something good about this model? Wheels are mortal, right? So if you're a wheel, that may not be good for you, but at least, when we're trying to model the real world, the fact that wheels die, or at least get removed from the Earth, is good. What's something that's bad about this model? No account for environmental stuff, everything is always the same. What you do is, again, walk before you run. And so we'll see how to solve something like this, and then you can tweak it and you can make it even more realistic. So does anybody have any thoughts as to how we might model this with a recurrence relation? So what would you want your variables to be? What would you want to understand? So one is we would want to just count how many wheels there are. And then we would want to know how many wheels there are at every moment in time. But what do you need to know if you want to figure out how many wheels are born at the next stage, or how many wheels die? Is it enough to just know how many wheels there are? You have to know their ages. So let's introduce some numbers or some parameters. Let's let AN be the number of wheels that were born at time n. BN will be the number of wheels born, that are 1 year old at time n. CN will be the number of wheels that are 2, and DN are the number of wheels that are 3. And then the number of wheels alive is just going to be their sum, but I'm going to split up into different populations. Hopefully you can see why this might be a good thing to do in a class that is eventually going to try to model COVID. trying to split a population into different populations and look at how they interact. And what's going on here is we'll let Vn be the vector of how many wheels we have at each age at time n. Vn plus 1 will be how many we have at time n plus 1. And then we have a relation that tells us, using linear algebra, Vn plus 1 is AVn. So this is telling us how we move. Let's think about what this means. So if I put my vector AN, BN, CN, DN here, how many wheels, what happens to all the wheels that are 3 years old? What happens to them 1 year in the future? They die. They have nothing to do with what happens. They die. Like, how do we know how many wheels are born? What do we look at for that? So I'll put my stuff over here. So we want to calculate AN plus 1. This is how many wheels are born in year n plus 1. Who contributes to wheels being born? I'm sorry? The wheels that are capable. So do any of the wheels who were just born the year before, do they contribute anything? So they would just be a 0. What about the wheels that were 1 year old? Do they contribute anything? Yeah, they contribute 2. And what about the wheels that were 2 years old? Do they contribute anything? They contribute 1. And then the other wheels won't do anything. And so that tells us how many wheels we have at time n plus 1 from how many wheels we had at time n, who are now just born. Now we have to figure out how many wheels do we have at time n plus 1 that are 1 year old. What would that just be? The wheels that were just born the year before, so it would just be 1 AN plus 0 BN plus 0 CN plus 0 DN. What about CN plus 1? What would that be? I want to know all the wheels who are now 2. Right, so everything just moves up by 1. And so we actually get a nice system of equations. And that tells us how many wheels we have at time n plus 1 of each age in terms of the previous. Yes? So because they're dead, they're no longer in play. So we could actually keep track of all the wheels that have died, and then that would constantly be going up. But if we want to know how many wheels are alive, we only have to worry how many were born, were 1 year, were 2 years, were 3 years. Yes. And so once we have this, here is our model. And if you've seen linear algebra, this is just writing it in matrix form. If you haven't, then just write it this way. And then the question is,
The last one is 1 CN.
More complicated than the Fibonacci's, and it's beginning to take into account various things. If you want to make this even better, what you would do is you would replace these 2s and 1s with random variables, so that you don't always have 2, you don't always have 1. And over here, you would replace 1 with a random variable that's at most 1 to take into account that some wheels die and don't live to be 4 years old. And so you would have a matrix that's now random. This is a very different model. This is completely deterministic. Okay. And so it turns out that we can solve something like this. And so one of the hardest things to remember is that sometimes you don't always look at the right problem. And then instead of doing the Fibonacci numbers, maybe we should have started with something easier first. Instead of a relationship that goes 2 day, maybe I should have said an plus 1 is just some constant times an. And that's going to be a much simpler relationship. So you just multiply your previous value by C. Okay, so if I was 1, I then go to, well, it depends what C is. So what if you want to make C 2? So if C is 2, you go 1, 2, 4, 8, 6. So this is very easy to solve. Structurally, this kind of looks like that. My vector is a fixed matrix multiple of the previous. And there are ways to solve that as well. There's very nice generalizations of this dumpling. So I'm not going to go into that now, but there are ways to tackle problems like this. And so I'll be assigning some problems related to this. But we have 1 minute left. I just want to end with a question for you to think about. So let's add an even more advanced model. Let's assume that there are only 2 species in the world, rabbits and foxes. What do you think foxes do? Eat the rabbits. What do you think the rabbits do? I'm sorry? They run away. They try to survive. So the question is, how would you model how many rabbits and how many foxes there are at a given time? You don't have to be able to solve your model, but try to come up with something. We'll assume a discrete model. You know how many rabbits and foxes you have at one time, and then you want to see how many you would have one step later. And when you're doing this, there can be a tremendous number of features that go into play. You might actually be worried about the fact that, well, if we have too many rabbits, they will be competing with resources for each other. And so you might want to include that in your model or not. All right, so I'm going to stop the recording here.